A few weeks ago, I was doing some hi-fi amplifier testing with the Analog Discovery 2, and in part of that I talked about but didn't actually measure harmonic distortion when I was using the spectrum analyzer to look at the harmonics of a signal. But it occurred to me that at the time that it probably would be a good idea, before I tried to use the Analog Discovery 2 to do harmonic distortion measurements, to find out exactly how much harmonic distortion that the Analog Discovery itself has, because nothing is distortion free. So what I have done is I've hooked up the Analog Discovery. I've set a 1 kilohertz sine wave on the wave generator, and then I have connected that over to my Rigol DS4000 so I can monitor the signal. I am now going to come over here to this instrument, which is the Hewlett-Packard 334A Harmonic Distortion Analyzer, and I'm going to try to measure the distortion on the Analog Discovery 2. But before I do that, I think it would be helpful, particularly for those that might need a little review on harmonic distortion, to at least talk about the basics, what it is we're going to measure and how this instrument does that. So let's take a look at that first. If you look at a pure sine wave on a spectrum analyzer or other frequency sensitive device, what you will discover is that a pure sine wave produces a particular amplitude at only one frequency. If there are harmonics, then that is not a pure sine wave. So we assume that we're using a pure sine wave to measure harmonic distortion, and as you see in a minute, that does change our reading slightly if it's not a pure sine wave. So one of the things you want to determine is how close to a pure sine wave is the generator you're using to measure harmonic distortion. Now, amplitude, when you're measuring harmonic distortion, is normally measured in RMS volts. However, occasionally in this experiment, you'll see me using peak or peak-to-peak voltages, and that's because, for example, the Analog Discovery 2 reads out in peak voltages. So we can convert that to RMS for a sine wave by multiplying by 0.707. But at any rate, what we're going to be trying to determine is, in the real world, there is not only a fundamental, but also harmonics and, shown here as little squiggly lines, noise. Now, you have to live with the noise. You can drive it down as low as you want, but you can't get rid of it. But what you can do is use a notch filter to get rid of the fundamental. Once you've done that, everything that remains, the noise plus all the harmonics, represents the distortion, or what is called the harmonic distortion. Now, if you look at this next diagram, you see what I'm talking about. Here, you sum the voltages after you have notched out the fundamental. Notice that it's missing down here. So you have harmonics and noise, and you then add up the voltages. In other words, you do an RMS, a root mean square computation. That then gives you a figure for the noise on the output of the amplifier plus the harmonics on the output of the amplifier, designated here by 2. The input would be noise 1 plus harmonics 1, which we are assuming for now that the noise is negligible, close to zero, and can be ignored, and the harmonics are zero at the input, which they really aren't, but we'll ignore them as well. Therefore, we're just looking at the noise in the output plus the harmonics in the output. We divide that by the original signal plus the noise and harmonics. This is generally the way you measure the percentage distortion, that is, the percentage of harmonic distortion, sometimes called THD, or total harmonic distortion. So how do you do that? Well, the first thing you do is you put your generator through your harmonic distortion analyzer and determine what the percentage distortion is of just the generator. Then you insert your amplifier and measure with the same generator settings. You measure the harmonic distortion with the amplifier inserted. The difference between the percentage distortion of the generator and the total distortion of the combination is the percentage distortion of the amplifier itself. For our purposes today, we're only going to be doing the first one of these, because what I'm really trying to find out is how good a generator is the analog discovery too. To do that, I'm going to use two different harmonic distortion analyzers. The first analyzer that we'll use is the Hewlett-Packard 334A, which is an old school analog distortion analyzer. The way it works is this. The first thing you do is you set the level of the signal from the generator or from the output of the amplifier, whatever the signal is. You put this in the set level position and this in the set level position, and then you adjust these controls until your meter reads maximum, if you're trying to read percent distortion. And I won't get into the directions. There's a slightly different setting if you're trying to measure distortion in dBm. But we're going to use percent distortion, so we set the meter to full scale. Then we go to the distortion position and we adjust the frequency of the notch filter for a null. You also have to balance the bridge. It uses a Wien bridge. Now I've been going back and forth between the frequency setting of the Wien bridge and the balance of the Wien bridge until I got the lowest reading I could get. At that point, you lower the reading and read off of the scale here what the full scale reading is. In this case, it's 0.0003. So up here, at this 3 position, that would be 0.0003% distortion. So our distortion is around 0.0002%. That is an incredible distortion reading. But since there's possibility, this is an old generator or an old analyzer, harmonic distortion analyzer, maybe it's too generous. So let's switch over and use a different method of measuring total harmonic distortion. We're going to use the Keithley 2015. So let me set that up. The Keithley 2015 THD multimeter has a percentage distortion, that is a THD measurement function built in. I won't go into the details of this, but I have set this up so that The input from the analog discovery is over here, and the instrument has already been adjusted so that it will automatically sense the fundamental frequency. It does this digitally using a fast Fourier transform. Then it removes the fundamental, just like the Wien-Bridge did in the HP unit. That is, it's a notch filter, only in this case it's a digital notch, and then sums the voltage of the other components, including the noise, and displays that as a percentage of the fundamental. As you notice, it's reading 0.01 and it's jumping from about 0.012 up to 0.016. That's partly because of the noise and other things in the system. But what you see here is, while it's not showing quite as low a distortion as the Hewlett-Packard, it is demonstrating a very low distortion. To give you a comparison, what I'm going to do now is disconnect the analog discovery and connect the Keithley's own internal generator, which of course is designed for low distortion, operating at the same 1 kilohertz frequency. We have to allow it to finish up, and you notice that it's reading 0.015, 0.016. Now, one reason that this doesn't jump around quite as much as it does with the analog discovery is when you're using the internal generator, the auto function is more efficient. That is, it's a slightly narrower window, and as a result, it doesn't tend to, the auto frequency find function for the fundamental is a little tighter, I guess is the way to put it. But nonetheless, you notice that the distortion that it is showing is essentially the same as the analog discovery. Once again, what this tells me is that the analog discovery 2, at least at a kilohertz with a sine wave, has such low distortion that it is a perfectly appropriate unit to use for THD measurements. Now, since I have the Keithley, and since I also have a very low distortion generator up here, this WaveTech, which is another old school electronics gadget, which has extremely low distortion, I don't actually need the analog discovery for this purpose. But before I could recommend that you use the analog discovery 2 for distortion measurements, I felt like I needed to verify that in fact its output is pure enough from a spectral standpoint to do an effective job measuring total harmonic distortion in amplifiers and other devices. So I have sort of reached the end of what I intended to do here. At some point in the future, I may use the analog discovery to do THD measurements. I might also, for other reasons, do a little bit more on the Keithley, which I just got recently. But for now, I think that I'm going to wrap this one up and declare that the analog discovery 2 output waveform is as spectrally pure as the Keithley. I, by the way, did not show you on camera, but I also measured the Keithley on the HP, and it measures as low as the analog discovery. That is extremely low, down in the 0.000 percentage. Hope you enjoyed this, and I hope it will give you a little confidence in the output of the analog discovery. And I encourage you to use it for this purpose or for any other purpose that you see fit. So stay tuned for some future videos. This won't be the last on the analog discovery 2, But it certainly is an example of what a great instrument this little AD2 really is. So have a good day, and we'll see you later.